Hi everyone, welcome back to the channel. If you are a beginner looking to get into software engineering, or if you are trying to crack interviews at top tech companies, you have probably heard these three letters: DSA, data structures and algorithms. But let's be real, looking at the sheer amount of topics can feel completely overwhelming. Where do you even start? Do you need to learn math? Which programming language should you choose? So many questions like that. Well, look no further. In this video, I am breaking down the absolute best, most definitive DSA roadmap for beginners. So we are going to go from total newbie fundamentals all the way to advanced problem solving techniques. So I have broken this down into clear, structured phases so you can save months of wasted time and frustration. So grab a notebook, hit that subscribe button, and let's dive straight into phase 1. So before you can write an algorithm, you need a tool to write it in. So step 1 is simple. Pick a language. A common trap beginners fall into is switching languages constantly. Don't do that. Pick one and stick with it. The roadmap gives you great options like C#, JavaScript, C++, Java, Python, Go, Rust, and Ruby. If your goal is pure competitive programming or raw execution speed, you can start with C++ or Java. These are fantastic choices. Or if you want a smoother learning curve, you can start with Python. And I would personally suggest beginners to start with Python. Or you are focusing on web development, then JavaScript works too. So once you have picked your languages, you need to master programming fundamentals. Do not rush this. You need to be incredibly comfortable with these all things, like language syntax. So knowing how to declare variables and write clean code, it would be help you a lot. And then control structures, like understanding if-else conditions, for loops, and while loops. Then functions. Functions are like how to break your code into reusable blocks. And then OOP basics. It is actually object-oriented programming concepts, like classes and objects. And finally, pseudocode, which means sketching out your logic in plain English before you actually type out the syntax. Now that you can write basic code, so phase 2 is about understanding what data structures are and why they are important. Simply put, a data structure is just a specific way to organizing and storing data in a computer so that it can be accessed and modified efficiently. Think of it like a kitchen. You would not store your spoons in refrigerator, right? You put them where they make sense. So data structures are the same thing for your code. So you need to start with the basic data structures like arrays, linked lists, queues, stacks, and hash tables. So arrays are sequential list of items stored right next to each other in memory. And then comes to linked lists. So elements that points to the next element and scattered across memory, they are linked lists. And then we have stacks. Think of a stack of books. Last in, first out. It's simple. And then we have queues, like standing in a line at a music concert or a coffee shop. First in and first out. And then the hash tables. So hash tables are key value pairs that allow for lightning fast lookups. So now, once you know how to store data, you need to measure how good your code is. So these bring us to algorithmic complexity. You must learn how to balance time versus space complexity, meaning how fast does your program run and how much memory does it use. So to express this, we use asymptotic notations, specifically big O notations, the worst case of scenario, and then big theta notation, the average case, and the big omega notation, the best case scenario. And then you will need to memorize some common runtimes from fastest to lowest, like constant runtime or order of 1, logarithmic runtime like order of log n, and then we have linear runtime, it is order of n, and then we have polynomial, order of n square, and then we have exponential, order of 2 to the power n, and then factorial, order of n factorial. Alright, you have your data structures and you understand big O. Now it's time to learn how to manipulate the data using the two most classic problems in computer science, like sorting and searching. So let's start with the searching algorithms. If you want to find an item in a list, you have two core options like linear search and binary search. So in linear search, checking every single item one by one. It's simple but slow. So its runtime is order of n. And then we have the binary search. So it is the ultimate divide and conquer search. If your data is already sorted, you can repeatedly split the data in half. So this is incredibly fast and it run in order of log n runtime. Order of log n. And next we have the sorting algorithms. Here you need to learn how this work under the hood. So like the basics, bubble sort, merge sort, insertion sort, quick sort, selection sort, heap sort. These are much more efficient and they are running in order of n log n time and are what real world languages are used under the hood. Now we are entering intermediate territory. Linear structures like arrays and linked lists are good, but real world data is often hierarchical or interconnected. So first we have tree data structures. A tree has a root node and child nodes. You will be studying binary trees and binary search trees, where the left child is smaller and the right child is larger than the parent. And self-balancing trees like AVL trees and B trees or heaps. You must master the tree traversal to visit every node. This includes BFS or breadth first search using a queue and depth first search or DFS, which breaks down into three flavors like in-order traversal, pre-order traversal and post-order traversal. And next, expand that concept into graph data structures. Think of a graph like a social network. Nodes are people and edges are friendship. You have directed graphs like Twitter, where you can follow someone but they don't follow you back, and undirected graphs like Facebook, where a friendship goes both ways. If they accept your friendship request, you become friends. So for graphs, you will reuse BFS and DFS for searching, but you will also dive into complex algorithms like shortest path algorithms, where you will learn Dijkstra algorithm, Bellman-Ford algorithm. This is literally how Google Maps finds the fastest route to your house. And then minimum spanning tree, where you will learn Prim's algorithm, Kruskal's algorithm. Once you have trees and graphs down, you can level up to advanced and complex data structures like trie, segment trees, Fenwick trees, disjoint set, or suffix trees and arrays. These are highly specialized and often requested in advanced system design or senior level interviews. So on this advanced side, you have trie, a prefix tree used for autocomplete search bars, and then you have segment trees and Fenwick trees used for efficiently calculating range queries, and then we have disjoint set. So it is great for tracking connected components, and then we have suffix trees and arrays. It is incredible for advanced string matching. And if you look at complex data structures, you will see 2-3 trees, B or B plus trees, skip list, ISAM. These are heavily tied to indexing, whether it's linear or tree-based, and form the bedrock of how modern databases pull up information in milliseconds. Alright, you know the structures, you know the algorithms, but when you open lead code, you still get stuck. Why? Because you have not mastered problem-solving techniques. So to track coding interviews, you don't memorize solutions, you memorize patterns. Here are the essential techniques our roadmap outlines. So the fundamentals like brute force, just getting a work solution, or recursion, where functions calling themselves, and backtracking, trying a path and backing up if it hits a dead end. Then we have divide and conquer, where we split a problem into smaller sub-problems. Then greedy algorithms, making the locally optimal choice at each step. Then dynamic programming or DP. It is the boss battle of DSA. It's just recursion but saving the answers to sub-problems so you don't recompute them later. Then we have specific coding patterns that unlock hundreds of interview questions like two-pointer technique and slider window technique, essential for array and string problems. And then fast and slow pointers, great for linked list cycle detection. Then merge intervals, cyclic sort, two heaps, and finding the kth element. And finally, niche patterns like island traversal, randomized algorithm, and multi-threaded processing. So this is a lot of information, but remember, you do not need to learn this all in 1 week. Take it phase by phase. To actually get code, you need to practice. The roadmap highlights excellent platforms to practice, including Lead Code and NAB. Start with easy problems, build consistency, and slowly work your way up to medium problems. And once you have conquered DSA, the learning doesn't stop. You can continue on to computer science core fundamentals or system design, which is exactly where you want to go next if you want to build massive and scalable applications. So if you found this breakdown helpful, give me a thumbs up, drop a comment, let me know what phase you are currently on, and don't forget to subscribe for more tech roadmaps. Keep coding, keep practicing, and I will see you in the next video. Thank you.